Good morning, everyone. Today, we will talk about how non-parametric classifiers generalize better to temporal changes in social media. I know it's a long title, sorry about that. So let's start. First of all, this is a joint work with some collaborators from UC San Diego, CMU, and Twitter. Let's begin with a question. How many of you train a model and it worked quite well in an offline scenario with offline data sets? You deploy to production and it start behaving quite bad. Does it happen to you before? It happened to me too. It's really frustrating experience because you put a lot of emphasis there. So it was so interesting, a so interesting problem that I wanted to dig and understand more what was happening behind. And this talk is a result of this experience, and I will share the findings with you. So what is the problem? Our language and our world actually is open-ended, not stationary, and also changes over time with recent events, news, and trends. It's no surprise that many social movements actually provide new words to our vocabulary. And also, it kind of shapes the words that we use every day. As a result, the world around changes with time, so what we talk also changes. For instance, you have this hashtag here, right? Indie keeps creating. However, it's very likely that this word is not part of your vocabulary unless you retrain it and actually use it to understand the full meaning of the sentence. So language models become increasingly outdated over time, preventing from temporal generalization. What does it mean? It means that sometimes you train a model in February with social media data, and you realize that there are a lot of interesting hashtags like Valentine's Day gift, or dating advice. You don't touch it anymore, and in May, you realize that there is a new song from BTS, or there are elections in Ethiopia, or there are some news related to some specific stock. Even worse, in December, you realize that there are also other important events, like the birthday of Taeyong, which is supposed to be a BTS singer. And also Christmas, of course. So, if it's not clear yet, we are talking about social media NLP, where we have user-generated data which changes because of new trends which influence online discussion. Then we have temporal adaptation issues for deployed models. Indeed, your model is always changing, so you may retrain it, but actually it's a costly process, and you don't really know when is the best time to do it. So language models become increasingly outdated over time because of several reasons that you probably already know. For instance, changes in factual knowledge, a new president in your country, seasonal events like Valentine's Day or Christmas, and even underlearned subpopulations in your dataset. For example, a new popular song from BTS or a famous paper and news. By the way, I don't like K-pop necessarily, but it's surprising how we find BTS data every time we train a model at Twitter. So, in order to deal with this problem, our deploy models have to implement two capabilities. The first one, to adapt to changes in the distribution. And the second one, to comply with privacy policies and regulations. I will stop here because this point is extremely important. Sometimes we don't really understand the implications that someone actually delete his or her account or her data or a post in a social network. If you remove a post in a social network, that means that that particular post should be also removed from any training data set in a company. And also, it should remove from that train model that is in production and that incorporated this information. It's actually very tricky to implement. So, users remove a post, a user deletes his or her account, and even companies actually remove existing content because it may contain harmful or toxic content down there in the data. So, to formalize the problem a little better, we have the task to evaluate neural models, but we train with data collected in the past, then we deploy the model, and realize that we are now testing the data from the future. This mismatch between the past and the future needs to be addressed with temporal adaptation methods. So already you will say, okay, deep neural networks already deal with this, either by fine-tuning a model or by deleting the user data and retraining from scratch. That's true. The problem is that it's very expensive. So can we do this cheaper, faster, and better? The answer is yes, and I will tell you how. First, there are some existing challenges when we evaluate models. The most obvious one is that actually you have new elements in your vocabulary, new words, new hashtags, new classes, new objects, new entities, you name it. You name it, you get it. So we have out of vocabulary elements that actually will hinder your predictions and will require you to train again. The second one is a little bit more interesting because people have shown that there are existing data leakage issues in the data set that we collect to train and also to evaluate our models. For instance, in 2021, Patrick Lewis actually saw that there exists a huge amount of overlap in existing question answering datasets, both at the level of questions and answers between 30 and 60%. That means that, for instance, if you have a question in the training dataset, like where is the Isthmus of Panama located, in the testing dataset you will have something like where is the Isthmus of Panama located on the map? And of course the answer is Costa Rica, but there is a data leakage problem here. As a result, your model will memorize the existing question, which is really bad, because if you actually use a model, train on this data, and evaluate it using this as a benchmark, it means that you are actually optimizing for the wrong metric. Because if you deploy it in production, you will have very bad results because of this memorization issue. Now, let's talk about machine learning. Existing regulations, such as the General Data Protection Regulation in Europe and the California Consumer Privacy Act in US, implement the so-called right to be forgotten. That means that we as developers and companies should take reasonable steps to achieve the erasure of personal data concerning users. In other words, as we use ML extensively to process data, we require to implement the right to be forgotten requirement despite of the memorization issues that we already saw in the previous slide. There is a nice paper introducing this concept 2 years ago. I require you to actually to read it. It's quite interesting. And it shows how hard it is to implement this requirement. For instance, if a user wants to delete his or her account, so this data is not available for training, you quickly realize that the data is actually spread out over time in different temporal partitions. So it's computationally expensive to actually not only delete the data, but actually to track which of your checkpoints incorporate this information. They come up with a very smart idea. They said, okay, let's divide, rather than partition the data by time, let's divide the data in shards, which are independent, and user data is actually only contained in one of them. They actually train an individual model for each of the shards, and every time there is a change for user U, basically it just update the shard, retrain the model, and the predictions come as an aggregation of the individual predictions that you have for every chart. Very smart idea. The problem is that if you actually do this very often, you will realize that some of the charts become so small. So the related models will become weak learners. On top of that, if you have small data and you have a highly parameterized model, what happens? You have overfitting, right? So very bad idea if you actually do it very frequently. What we are trying to do is to solve both problems, to do machine learning as well to deal with memory adaptation in a very simple way. For that, I want to talk to you about KNN language models. KNN language models have achieved remarkable success in the last years for problems like open domain question answering, pre-training of large-scale language models, machine translation, candidate retrieval in recommender systems, and so on. The idea is quite intuitive. We have a text encoder, and then the text encoder interacts with a similarity index. So this similarity index indeed extends the capabilities of the text encoder by linearly interpolating over tokens or sentence embeddings. So for instance, if you are working with machine translation and you want to predict what is the next token during your inference process, you will add more diversity by actually interacting with a similarity index and feeding the model with more tokens that will actually just enrich your set of candidates. Very powerful technique, and indeed we use it for temporal adaptation. So without gradients, we can actually have a non-parametric classifier that implements by retrieving tweet embedding from data stores and choose the best corresponding hashtag. What does it mean? It means that if we have a text encoder, we can just find the most relevant text embedding and use the associated hashtag as a class to provide a hashtag classification. If we exchange data stores over time, we demonstrate in the experiments that KNN classifiers is the best option for both temporal adaptation and machine learning. And we compare it to relevant parametric models like hashtag classification, hashtag sequence generation, and simple re-ranking methods. Of course, to facilitate the future research in this area, we're talking about the real-world deployment of NLP systems using non-parametric techniques. We share code and data set with the community in the following link. The data also needs to be organized in a different way. We have temporal buckets where the first 3 weeks correspond to training data, and only the last week corresponds to testing data set. So if you have a model, what we do is to actually evaluate in the last week of every month to track how the model is behaving over time. The data set that we share contains 7 million tweets from 2021 divided in 12 different buckets. There is a week related data between tweets and hashtags, and also 10K different hashtags per week. In total, we have 48 weeks of data. So to explain this in a more visual way, we have 2 relevant stages, the encoding stage and the deployment stage. In the decoding stage, you have the data divided into different buckets, one for each month. Remember, we are trying to provide hashtag classification here. So we have a trained text encoder, in this case BART, which is only trained once in the first available bucket. Since we are in the encoding stage, we can pre-compute existing embeddings for every bucket. So we end up with 12 different data stores. After that, we just create a similarity index in like 45 minutes, using, for instance, the face library from Facebook. This is a similarity search that provides and uses product quantization for similarity search. So in the deployment stage, your model now actually deals with new data. So every time a new data comes, the static text encoder that we use in the first beginning and we don't retrain further actually provide query embeddings to the similarity index. So the index will provide K candidates that minimize a distance function. We can rerun these candidates based on a notion of distance or frequency and provide the most similar one and the hashtag associated to it as a prediction. That way, you don't need to pre-compute or you don't need to retrain anything because you are just playing with existing pre-computations of tweet embeddings. If you want to implement machine learning, you just need to mask out some of the related examples that come from a particular user and just recreate the similarity index again. So this process is like 45 minutes. However, if you actually use competing baseline models for this, you realize that, for instance, using BART large encoder for multi-label classification takes like a day in one single GPU. And if you fine-tune a BART large encoder decoder, it will take like a week again in one single GPU. Compare the 45 minutes for this process versus a week of training or a day of training for a classifier or a sequence-to-sequence model. Of course, we also need some experimental configurations. For instance, we have the notion of not having time at all for experiments, where we have different buckets and we aggregate the different training splits for every month into one single training data set. And we also aggregate the testing weeks into one single testing data set. And this is pretty much the case where you actually have a model, you train in an offline setting, and you provide results. However, we will show later that this is actually hiding a lot of the temporal issues that could happen to your model. In the second setting, we actually have time information here. However, we don't implement adaptation, meaning that we train the model once in the first available bucket, and then we evaluate the model every month using the last week. This is the cheapest method, but it's also the less accurate. And finally, we have a notion of adaptation, meaning that we train the model every month, and we also test it in the following week. The results show several things. For instance, if there is no temporal shift, classification is just your best option. However, this is hiding some important information that we will see in the following slide. If there is temporal shift, with or without adaptation, the KNN language model is your most accurate choice without retraining, meaning that if you actually train the model once in January and you don't touch it again, but use a similarity index to provide candidates, you can have actually plus 3.6 higher recall points in your experiments over the sequence-to-sequence method. For instance, if we don't have adaptation, right, in the lower part of the figure, here we actually train the model only once in January. And you can see how the temporal shift kicks in. All these models are actually going lower and lower in accuracy because during inference, the testing data set is also more and more different. In this scenario, our approach of using a KNN language model actually is more accurate. The same happens if we have temporal adaptation, meaning that we are retraining the model or the text encoder every month. And still here, using KNN language models is a good idea. It shows actually the highest and more accurate results. Something interesting here is that if you actually do not want to retrain the model, sequence-to-sequence methods are actually more accurate than using just classification. Mainly because the sequence-to-sequence model will generate classes or will generate hashtags in this problem. So it will deal better with out-of-vocabulary classes. Also, remember we talked about what happens if we remove user data. So in this experiment, we remove 20% of user data, 50% of user data, and still it shows higher recall than the bar classifier, for instance. So using a similarity index to enhance your text encoder is also a good idea to actually have models that are less sensitive to user data deletion. So some conclusions here that I want to share with you. This is a thought that I have in mind in the last 2 weeks, given different events that we have seen in the news. I think that there is a huge opportunity for the LatinX in AI community to create cheaper, faster, better, CPU-friendly AI. What I'm talking here is that as we see in these current economic situations where actually there are a round of layoffs in companies, and actually I am from Peru and you are probably from a country in Latin America, companies have a huge amount of time to actually decide if they want to invest in AI because it's expensive. Having GPUs in production and development and to maintain it over time to retrain models or to just provide real-time inference is actually expensive. Over time, you will realize that there is a doubt between either investing in AI, which is expensive, or actually deal with the existing methods that only use CPUs, for instance. So my point here is clear. Probably as a community, we actually need to come up with better algorithms that are different in the sense that they are constrained to CPU only. Probably that way, we will create algorithms that may impact better our communities in our countries. It's good that we understand that if we invest in GPU, if we invest in deep models, actually it will be expensive to also use it in industry. The reason why I chose this topic to share today is because I feel it's more compatible with Latin America. I could have shown you here a huge model that we train over 16 GPUs with 1 billion data and have very accurate results. However, sometimes that's not how reality works. Even if you have a huge model, you need to make it smaller, even with product quantization, which could also take weeks to come out with a relevant model with a similar performance. So this is just to raise the concern that in reality, these huge models, especially in the context of Latin America, may require to be efficient. And this is probably a huge opportunity for LatinX and AI researchers to create more CPU-friendly algorithms that work actually faster and better. Along those lines, our method is cost-effective in the sense that it implements temporal adaptation. It removes user examples from trained data to implement machine learning, and it showed huge savings in computational cost. I told you before, fine-tuning a sequence-to-sequence bar model for this problem took a week using one single 800 GPU. But just creating the index takes like 45 minutes in one single GPU, and it still shows better results with higher recall at 5. We compare for this matter with 2 neural parametric models, and we show the higher recall in the presence of temporal shift. And finally, we share our code and benchmark dataset for hashtag prediction, which contains 7 million tweets from 2021 split into 48 weeks. You can find the code and the papers in this link again. You can also contact me later so I can give you more details, or we can discuss more about this work. But I just want to tell you now, thank you and gracias.
Thank you, Dr. Flores, for the exciting talk. I am a little bit excited to I'm a little bit interested to ask you, like, how did you make sure when you are learning, you are based on a similarity, you are not deleting useful data which might be similar to your previous data? Like, how did you make sure of that?
That's a great question. Can you hear me? Awesome. So that's a great question. So here in this experiment, what we do is to have different settings for this experiment. For some of them, we randomly remove user-relevant data for a particular user. In some cases, we deleted also all the data for a particular user. So defining what is relevant or what is not is probably hard to do that beforehand. We just assume that the random removal of user-related data will be enough here. But in reality, you are right. I mean, users probably want to delete some information that are recent or some related to some topic. I can just tell you that a random deletion was fine, and also a user-related deletion, meaning that all the posts for one user were also removed. And in all of them, it actually showed a comparable result as well. But that's a good question and probably a follow-up experiment. Thanks.
Hello, very interesting talk.
Thanks.
So one of the questions that I have, when you actually do the nearest neighbor, how do you try to create new clusters in the case of explicitly new information is arriving, and probably before it was part of one of the clusters, and then becomes a single out because it becomes trending or something like that? How do you try to manage this in automatic way?
Correct. The creation of the index is actually offload to Phase. Phase actually deals with that by creating clusters first, and then kind of filling this cluster in a way that we have a linear query search time. So this process happens inside of Phase. Phase is a really amazing library that can scale up to 1 billion and billions of records. However, it's prone to the order of the elements to fit the similarity index as well. There is no much waste in actually retraining the index every certain amount of time, or just creating from scratch. Creating from scratch takes like 45 minutes in our experiments for this size of data. There are the option also to update the existing index, which takes like a couple of minutes only. So to answer your question, I would just rely on a random insertion of elements in the similarity index, knowing that it's actually so fast to create. Thank you.
One more question in the back.
So thanks for the talk. I have a question which is kind of related to the KNN talk and also to the LatinX talk that you said later, because did you measure, or can you at least share with us some information on how the amount of data impacts your method? Because when you do natural language processing for, let's say, Portuguese, you don't really have enough data. So could a method like this work there, like the KNN, or is it more related to having a whole bunch of data?
I love the question. Here, for instance, we have BART, and BART is only trained on tweets in English, right? However, it could be MBERT, it could be another multilingual text encoder. And we have seen in production the amazing capabilities of multilingual models to rely on cross-lingual capabilities to actually still, for instance, provide predictions in Portuguese based on Spanish tweets, for instance. So I will say that it will only make the result better to rely in other languages, but it depends on the text encoder. For this experiment, it was only English, but in different problems, we have seen like amazing results for underserved languages, and we saw that, for instance, I can say much details, but for instance, in a particular use case in Germany, based on a multilingual model that was trained with a lot of data in English, it showed amazing results with only probably 2 degrees of error in comparison to just using, for instance, tweets in German or something like that. So yeah, I would say just replacing the text encoder in this setting will accommodate for using other languages as well. Thanks.
Hi, thank you for a really, really great talk. I was wondering if you have a sense of like how long this would last, like how robust it is to domain shift. So you've looked at a year, but yeah, I don't know if you've tested this or thought about it.
Yes, indeed. I have a slide here as well. I just didn't present it because I thought we didn't have enough time, or I couldn't make it on time. Here in this ablation experiment, we are replacing the text encoder with different text encoders. For instance, BERT tweet and also just BART encoder out of the box. You can see how using BART encoder out of the box, meaning no domain adaptation at all, have really bad results in terms like 4 degrees of error here. Doing domain adaptation in the first month using the first bucket actually gives you a higher leverage here. So definitely it's important. What this is probably showing is that we don't need to do domain adaptation very frequently. We can only do it in the first month. Of course, all these experiments are in the span of 1 year. I cannot tell if we need to retrain once a year or something like that. What I can tell is that we don't need to retrain as often as using, for instance, a previous setting or a different setting. But to your question, for instance, using BERT tweet, which was, it's a very famous text encoder based on tweets, which was trained from 2012 to 2019, doesn't work quite well either because the data we are dealing with is from 2021. So this level of domain adaptation on time also is irrelevant for sure. Thanks.
All righty, thank you for your questions. Let's give thanks to Dr. Omar Flores for a wonderful talk.